In this video, we're going to continue our discussion of the normal distribution and step through a z-score calculation through an example that examines muscle strength in a sample of individuals. And so our sample in this particular example, here we have an average measurement of muscle strength of 40. Nm stands for the units Newton meter, which is a unit of muscle strength, with a standard deviation of plus minus 7 Newton meters among our sample. And so by examining our sample data, we assume the sample fits a normal distribution. And so what we see here are two x-axes. We see one x-axis in the original raw scores in Newton meters. As we can see here, the average is 40, and we haven't yet illustrated the standard deviation yet. But the second x-axis here are the same data expressed in z-score or standard deviation units. And so what we see here, where an average of 40 in raw units will equal a z-score of 0. And using the z-score scale, we can then map out the distribution of scores based upon how they are spread out in terms of 1, 2, or 3 standard deviation units. And we'll step through this example shortly. And so when we talk about the z-score, we can take any score in our sample and convert it to something called a z-score. But in order to do so, we need to know the mean and the standard deviation of that distribution or of our sample. So anytime we have a sample of data, we always start by calculating the mean and the standard deviation. And so the z-score calculation, what we see here is we take a raw score from one and only one person, and we subtract the average of the entire sample divided by the standard deviation of that sample. So once again here, the X represents a single raw score, X bar represents the sample mean, S represents the sample standard deviation. Now, if we had 30 people in our sample, we would end up with 30 z-scores. And the only difference between the z-score calculation for each person would be in the X. The X bar and S value would be the same for each person in our sample. So the advantage here in using a z-score, it allows us to assess the relative position of each unit in the sample. So it allows us to get a visual representation of where one person's score sits with respect to another person's score, as well as the group average. And as you can see here, if we have units of Newton meters in the numerator as well as the denominator, remember standard deviation units take on the same unit as the original measurement, the units will cancel. So this therefore allows us to compare between different outcome measures that have different units. Now, to gain a visual understanding of how the z-score and standard deviation maps out onto the normal distribution, we see here our normal distribution with just the z-score axis illustrated along X. Now, we always have our average value centered at 0, and if we wish to examine the data out to positive 1 standard deviations, so in other words a z-score of 1 unit here, then this would capture all the scores between the average and the positive side only of the standard deviation. And if we estimate this area with respect to the entire area under the curve, this area represents 34.13% of the entire area. Now, if we take this out to 2 standard deviation units, then we see that by moving our marker here from 1 to 2, we now expand the area under the curve, and the area under the curve represents how many people are in this, how many measurements or units are in this that make up this distribution. And when we expand out to 2 standard deviation units, the area here now expands to a set value of 47.72% of the entire area on both the positive and negative side. Continuing this, if we move our marker out to 3 standard deviation units, or a z-score of 3, those terms are used interchangeably, now we see a further increase in the area captured underneath the curve, only on the positive side, to be almost 50%, almost half of the entirety of this area at 49.87%. So these are fixed values of the normal distribution. Now, if we wish to capture the area under the curve from both the positive and negative side, so a z-score of negative 3.0 to positive 3.0. Recall that our standard deviation units, when we calculate them, are expressed in a plus-minus fashion. The previous examples, we only focus just on the positive side to illustrate the idea that the standard deviation captures how many people and how much variability around the average exists in our data set. So moving on here with a z-score between negative 3 and 3.0, we have our markers at negative 3 standard deviations, or a z-score of negative 3, a z-score or positive standard deviation side of plus 3, and we see that when we expand our examination of the data out to 3 standard deviation units, that will capture over 99% of all the samples within a distribution, within our sample or a population. Now, to move on to an example where we will calculate a z-score in this subsequent, that was something that we mentioned a little bit earlier. So we ran through this hypothetical study where a number of individuals were assessed for how strong their arm flexor muscles were as a measurement of torque. And so we have one person that measured out at 52 Newton meters. And so if we wish to know where this one person score sits with respect to the rest of the sample, we're essentially asking what percentile does this represent. And so the way we go about this is we calculate a z-score. So recall, one of the advantages of the z-score calculation is it gives us an assessment of where each individual score resides in terms of location with respect to the mean as well as other scores. So in order to calculate the z-score, you have to absolutely need the sample average. In this case, it's 40 Newton meters, as well as we absolutely need the standard deviation of 7 Newton meters. So we have our z-score equation, and we just look for the numbers that fit the variables or the symbols on the right-hand side. So the x is a given here at 52 Newton meters, and that's the one person we're interested in. Our descriptive statistics were already generated as we calculated the average and we calculated the standard deviation. So we just simply substitute those values, and so we have 52 subtract 40 Newton meters. 52 also carries the units of Newton meters, and we divide that by 7 Newton meters. And as a fraction, the units Newton meter and Newton meter will cancel out, so we end up with a z-score that does not have units. And that's an advantage because that will allow us, if we wish, to compare outcome variables along different scales to each other. So we go through our calculation and we find that we calculated a z-score of 1.71. And so what does this mean? Recall that when we talk about a z-score, we're using that term interchangeably with standard deviation. And so 1.0, a z-score of 1.0 is 1 standard deviation. This person that we factored into the equation, their score resides beyond 1 standard deviation unit on the positive side of the z-score. If this person's score was less than the average, then they would have a z-score that was a negative value. And so what we do here is we'll discuss this in a very brief but subsequent video, where we go to something called the normal distribution table. And it's a table of numbers that correspond to the z-score and the area captured underneath the normal distribution as a reflection of how many scores sit in that area. So if we go up to our graph here and we look along the x-axis, we calculated 1.7. So we just use a visual here. So we're just getting really just a visual estimate of where 1.71 would reside on this scale. So these ticks are pretty small here, but you can see we have the first tick here on the x-axis. That's positive 1 standard deviation. You see the 2 and 3 and 4, so on and so forth, and on the negative side, but we're just going to concern ourselves with the positive side for now, since our z-score was a positive value. So we see that 1.71 along the x-axis sits somewhere around here, and I just visually estimated that with my arrow. And so using this arrow, then 1.71 sits at this location with respect to all the other scores that were sampled. So this person's strength score was better than average, was stronger than average. We knew that because we had their raw score and we had the group average. But the question here is, how much better than average was this person's strength score? Well, their strength score existed beyond 1 standard deviation of our sample. And so if we wish to calculate their percentile, we're going to go ahead, I'm going to provide you the numbers here, and in a subsequent video I'm going to show you how these numbers were obtained from the normal distribution table. And so the percentile score is the sum of 50 and 45.64. Now, where did I get these numbers? Well, if you take a look at the green here, 50, that corresponds to the negative half of the normal distribution area. And so the area here represents all of the scores that were at and below the average strength of 40 Newton meters. So these were not negative values in Newton meters. These were just values that were less than 40 Newton meters. And the blue area represents all of the scores between the average and the person's z-score of 1.71, and the 45.64 value came from the normal distribution table, a table of numbers that corresponds, that matches up a z-score with an area. And when we add up these two, we find that this person's percentile ranking was at approximately 95.64 fourth percentile, which means that the person's strength score, or rather 95.64% of all of the strength scores, were at this person's value and below. So this ends our lecture here on the normal distribution and z-score.